Hello everyone, and thank you for being here today. Let me introduce myself. I'm Shraddha Shaji from DACS, and my group members are Sandeep, Adil, and Dia. We are group 2, and our topic is chaos theory and fractals. This is our problem statement. Explore chaos theory and fractal geometry and implement the secant method for root finding of non-linear equation using Python. Today we are discussing about introduction to chaos theory, application of chaos theory, fractals, applications of fractals, relationship between fractals and chaos theory, mathematical foundation, Python implementation, future of chaos theory and fractals. Introduction to chaos theory. Chaos theory describes the quality of point at which order moves to disorder. The phenomena of chaos theory was introduced by Edward Lawrence in 1972. In chaotic system, a tiny change in initial condition can lead to a drastically different outcome. I think you may be familiar with this key concept, that is butterfly effect. This is one of the most famous concepts from chaos theory. It suggests that a tiny change in one part of a system can lead to massive difference in outcomes. The term comes from the idea that flap of a butterfly wing in Brazil could set off a chain of events that results in a tornado in Texas.
So, I'm going to take I'm going to take the part of applications of chaos theory, and the first one is weather forecasting. The butterfly effect illustrates how small changes in initial conditions can lead to a varieties of vastly different weather outcome. For example, a minor change in forecast can even predict a disaster prediction. And the next is epidemiology. The spread of diseases like COVID-19 pandemic can be modeled using chaos theory. The next is finance. So stock market analysis often employs chaos theory. The fluctuation in stock prices can show unpredictable patterns, potential threats, and risks. Robotics. Chaos theory informs algorithms that allows us robots to navigate complex environments. For example, swarm robots can use principles of chaos theory and enable it to work in groups to work effectively. And the next one is market dynamics. Consumer behavior analysis uses chaos theory to understand fluctuations in demand. Thank you.
Fractals. Fractals are infinitely complex patterns that are self-similar across different states. So basically, fractals are shapes or patterns that look similar no matter how you zoom in or out. For example, if you look at a tree, you will notice that the branches look like mini trees. Then characteristics of fractals. They are similar, like they are similar in shape and structure. Scaling symmetry, meaning that they appear the same when viewed from different distances. Then non-integer dimensions. This means that they do not fit into the traditional geometrical categories of points, lines, and planes. Infinite complexity, meaning they have an infinite number of patterns and details. Types of fractals. Geometric fractals, algebraic fractals, natural fractals. So geometric fractals, they are created using triangles and squares. Algebraic fractals created using algebraic equations. The natural fractals, they are like the snowflakes, mountain ranges, even clouds. Then these are some famous fractal examples: Mandelbrot set, Julia set, and this triangle. Then applications of fractals. Computer graphics and animation, terrain generation, This is used to generate realistic landscapes, mountains, and clouds, like in video games and movies, by simulating the natural pattern like those in the nature. Then texture generation is employed to create complex textures for objects, surfaces, and backgrounds in CGI. Then modeling in nature, geographical modeling like models in coastlines, mountain ranges, etc. Then plants exhibit fractal growth patterns like in branching structures. Then medical imaging, analysis of biological structures. Then tumor detection. That in fractal analysis helps in detecting irregularities in medical images, distinguishing between the normal and the abnormal growth patterns. The fractals are essential in studying the chaotic system, in the weather patterns and the fluid dynamics. Then fractal is used to make designs, then fractal art, then astronomy, galaxy formation. Fractals are used to model the large-scale structure of the universe, including the distribution of galaxies and star clusters. Thank you. Forward.
Relationship between chaos theory and fractals. Fractals as visual representation of chaos. Fractals are complex, self-repeating patterns that visually show us how chaos can be organized. Unpredictability and infinite detail. In chaos theory, unpredictability is key. Even small changes in starting condition can lead to different outcomes. Self-similarity in chaotic system. In fractals, the structure looks the same at different scales. In chaotic system, the outcomes of iterations of the system can form fractal patterns. Fractal dimension in chaos. Both fractals and chaotic systems are characterized by fractal dimensions. Chaotic systems often occupy a fractal dimension in their phase space. Iterative process. Both fractals and chaotic systems are generated through iterative process. Fractals in nature as evidence of chaos, weather patterns, coastal lines, biological systems. Over to Adi.
Good afternoon. Myself, Ali Ravi, and I am from DCS. Here, Sabina, Dia, and Sandeep talked about chaos theory in fractals. And I am going to talk about the mathematical foundation of fractals using the secant method. And we know that we know about the Newton's method. In Newton's method, there is a function, and we should find the derivative of that function. And here, the secant method is almost similar to that of Newton's method. And it is an iterative root finding algorithm which approximates the root of the function f of x is equal to 0. And the formula is x of n plus 1 is equal to xn minus f of xn minus xn minus xn minus 1 divided by f of xn minus f of xn minus 1. And we should apply, when we apply in the secant method in the fractals, we are considering the function f of z is equal to z cube minus 1. And when we apply it in the secant method, it becomes z of n plus 1. Z of n plus 1 is equal to z of n Z of n plus 1 is equal to Z of n minus f of Z of n minus Z of n minus Z of n minus 1 whole divided by f of Z of n minus f of Z of n minus 1. And by doing the secant iteration, we get the roots as Z is equal to 1, Z is equal to e raised to 2 pi I by 3, and Z is equal to e raised to 4 pi I by 3. And the points near the roots, when the points near the root converge to any one of the values, we get a fractal structure. In the Python implementation, first we import the NumPy library for the numerical operations and the matplotlib.pyp LOT for creating visualization. Then we define the function, define f of z is equal to return z raised to 3 minus 1. And here we are defining the function f of z, which takes place in a complex number z and which returns zq minus 3. And the function has 3 roots in the complex plane. Then we are defining the secant method for finding the roots f of z in the complex plane. That is defining secant method z0, z1 max liter equal to 50 and tolerance equal to 1e minus 6. Here z0 and z1 are the initial guesses in the which are the complex numbers, and max liter is the maximum number of iterations allowed, and tolerance is the told is the tolerance level for stopping the iteration based on how close the consecutive estimates are. And the equation z2 is equal to z1 minus f of z1 into z1 minus z0 divided by f of z1 minus f of z0 is a secant formula. Then we are creating a grid of complex points over the region minus 2 to 2 and minus 2 to 2. That is, RES is equal to 500, which is the resolution, the number of points per axis. And we are giving the function np dot linspace, that is x equal to np dot linspace minus 2 to RES, and y equal to np dot linspace minus 2 to RES. Here it generates 500 points from minus 2 to 2. In both x and y axis. Then xy is equal to np dot mesh grid xy to create two grids, and z is equal to x plus 1j into y to create a 2D array as the complex numbers in the form x plus iy. Then iterations is equal to np dot zeros z dot shape, and roots is equal to np dot zeros z dot shape d type is equal complex. Here iterations are the number of iterations. Iterations means the number of iterations each point takes to converge, and the root to which each point converges. And the z dot shape gives the shape of the z grid. So these arrays match z in shape, match z in size. And we are giving the loops through each point of the grid, that is for I in range RES, for j in range RES, z0, z1 equal to zij plus 1 e minus 4. Here zij, it creates two initial guesses, z0 and z1. And root iter count is equal to secant method z0, z1. Here we call the secant method z0. So yes.
Just think of logically, like, nothing, like you already said, someone said here, Mr. Sapna said that, your steel plate will start from two nearby initial gases, and those two nearby initial gases, they diverge. Okay, that is the butterfly effect. So therefore, you are showing the chaotic property here. One initial condition you took, that is Zij, yes. Then another initial condition you took is Zij plus a small disturbance, that is 10 minus 4. So if you take 10 minus 4, those will be two tiny nearby initial gases. And you want to see how those evolve. That's what chaos is.
Then we create a flow to visualize iteration, that is flow dot figure, fixed size 88, and flow dot IM show iterations CMAP, Inferno, extend -2 to -2 here. PLT dot IM show iterations CMAP equal to Inferno displays iteration grid using the Inferno color map, and the extend -2 to -2 sets the floor boundaries to match the complex plane region. It adds a color bar and labels the displays plot. That is PLT dot color bar label equal iterations to converge. PLT dot title secant method fractal iterations. PLT dot x label equal RE. PLT dot y label IM. PLT dot show. Then we define a helper function that is defined root color. It takes a complex. Here it takes the complex root and checks its proximity to each of the three expected roots. That is, if np dot abs root -1 less than 1e minus 3, then it returns 0. And if it is root minus 0.5 plus 0.866 j less than 1e minus 3, then it returns 1. And if the root minus 0.5 minus 0.866 j less than 1e minus 3, then it will return 2. If not in this three condition, then it will return 3. Then we visualize the root regions or basins of attraction. Color is equal to np dot vectorize root color roots. PLT dot figure fixed size is equal to 88. PLT dot I'm show color CMAP is equal to cool warm extend -2 to -2. Here we use the np dot vectorize root color.
So my question is like, what is color difference? You know, the range of color difference. What is color difference? How is what is color difference?
Iterations. Iterations.
Color difference. You try to find, but what's in this? This is the range of colors. That's what I. What's the range of colors?
Yeah.
Those themes will converge. So then you could have at least three colors.
The points near that region, it will be in same color.
But
We have three roots, and the points near that roots will converge to any of the value, and the values converging to that value will be in same color.
yeah, so I'm asking what is the difference between, say, I could understand the right word. The right word has three different colors. And then I understand that there are three different roots. And in between their pockets, boundaries, their patterns. But on the left image, it is like golden image, like golden structures. Is that image I'm not able to understand why you have color protection. Got the question, right? Yeah. So, watching the structure. And why you like this? Why not the right block? Or how is it different from the left or right?
So it is for the easy understanding of the fractals.
Spend a lot of time, and I think it's very important. But I'm just using the common sense. The common sense says that you have a legend. You have a legend which is saying equations to convert, right? Yes. Yes. So based on that, it is color coded. Is it based on that it is color coded? So what it is saying, if you are here, if you are seeing something black color which is around here, that means there are zero equations. That means you started from here. Your initial guesses might be from here. Okay, then number of iteration increases, that is golden region. Those are the points where it is getting converged. That means you are reaching your root there. Like this is the experience.
Here, NP dot vectorize root color roots to apply root color to each element in roots, creating gridded colors. And close this grid using PLT dot IM show colors CMAP equal to Coulomb with a Coulomb color map. And the plot shows which root each point in the complex plane converges to, giving a fractal pattern with the clear regions. That is this. Thank you.
And the next is the future of chaos theory and fractals. And we have the first one is advances in computing power and simulations. That's the modern supercomputers and the quantum computers can use all these chaos theory and fractals for making the intense calculations more easy and more accurate predictions. And the next is applications in machine learning and AI. Chaos theory can be applied in AI so that it can also predict more accurate results for whatever intense calculation we have given.
Chaos is itself unpredictable. So how we can use it to predict? What is fractal inspired neural network? That is what it is. Fractal inspired neural network. Then how fractal geometry can improve the architecture of neural network is I also want to. Fractal is inspired neural network. Why neural network tries to be only like a bad why can't they fractal?
The neural networks are never ending structures. So, no, not even like
fire.
So, chaos theory can be helpful in that.
Yeah. Chaos theory, no, fractals.
Understanding complex biological systems like all the blood vessels and neural networks often exhibits the fractal patterns. And the next one is environmental and science application. That's better climate modeling. The combination of chaos theory with advanced computational modeling can enhance forecasting for extreme weather events and can also predict long-term climates. Fractals in technology and engineering. Like in this, for using more technology, we are using all these fractal applications in these antennas to detect wide range of frequencies, etc. And then exists quantum chaos and fundamental physics. Quantum chaos in quantum system. That's the while classical chaos theory deals with microscopic systems, such as studying how chaos may manifest in quantum system. And then exists philosophical and mathematical explorations. So last one. Uh, Philosophical and mathematical explorations. Chaos theory challenges classical deterministic views of the universe. Like future mathematical developments may continue to explore the balance between order and randomness. And then exists aesthetics and creative fields. This includes the music and literature, like chaos theory may find more applications in music theories, like where complex rhymes and rhythms and harmonies are designed. Thank you.
I don't know what they did.